I did have a couple questions about what these things specifically mean. So what I'll do is I'll load up exe. So this one, like really, you know, this is a disassembly, you know, command. So you can, I'm using objdump just because it gives me the nice command line view, but you can use, you know, you can use rows, you can use IDA Pro, you can use any sort of graphical disassembler if you want to. So what I mean with these is that, so number one, you aren't going to be able to find like a magic instruction where you can make a binary signature just out of, say, you know, one instruct, like in this case, this is 5 bytes for an instruction. You're going to want to make sure that you are marking, say, a block or maybe a couple of blocks or something like that. So for instance, this right here is a sequence of instructions that implements a portion of an algorithm. So it implements like one block of code, basically. You have 8 instructions. The sequence of instructions is move, followed by push, followed by move, followed by push, followed by 2 move instructions, followed by test, and followed by a conditional jump, which is a jump if not equal. So, you know, to dive into this deeper, and I'll go to the, so here's again the analysis. So I have like explanation of one of the things that when, so number one, you don't need to make all of the Yara strings, or I should say, you don't need to make them all be what I would call register agnostic or handle different register arguments. You just need to demonstrate at least one of the ones that you're doing, or I should say, let me rephrase what I'm trying to say. So if I decided this was a significant block for some reason, so we'll say I've already come to that conclusion. I do not necessarily need, I'm not necessarily expecting that every single one of these things be register agnostic or anything like that. So I'm not necessarily looking for every single different move instruction or anything like that. However, I would expect there to be some use of like register wildcarding. So you need to have it written in such a way so that, for instance, this is a great example because it's, for whatever reason, it's move EDI into EDI, so it's move data from register into itself. So I forget the significance of why they would do something like this, but it's totally legal to do it. You'd want to implement one that handles like moving data from any of the registers into themselves or something like that. You know, so you'd want to pick features like that and pick a feature like that from the block where basically you can demonstrate that it's matching 2 places in the code, or maybe 2 places across 2 different exe samples where the registers don't match up. So you just want to basically be able to demonstrate that works somewhere in the larger pattern or larger signature you're building. You don't necessarily need to have that be the case for every single instruction in the signature, although you might find it's easier if you do take that approach. I'll say that my practice historically has been, so this is kind of my 2 cents, is that when I want to match a block like this, so when I want to write code that attempts to identify a block, or when I want to write a signature that attempts to identify a block like this, my first approach is to try and come up with a way to make it so that I have the broadest matching possible. So I'm casting the widest net, and then I gradually narrow in from there. So in this case, this is a great example or I'll say maybe not that one, because I'll be totally honest, the reason this one exists is mainly this is setting up the frame, or setting up the function frame. But this instruction here might be switched with a different register at some point in some implementations of this for some reason. So I might want to look up the different push instructions that are possible for that and support and allow it to match all those. And this one's a single byte. So for instance, if it pushed EDI, or if it pushed EBX, or if it pushed, you know, one of those things, then I might want to support those. And so that's kind of all that I was really asking when it came to that, was rate a pattern where you do employ some sort of wildcarding or fuzzing, so that you can show me that it's matching in multiple, so that it matches at least in one spot in multiple different implementations where the registers are changed. Yes?
So what you're saying is that if you go back to
the code.
Yeah. So like maybe it'd still be like a 55
Mm-hmm.
and then a push, but instead of EDP in one file, it might be like EAX or something.
Right, but then the 55 code would be a different code. So it'd be like 50 or something, or I don't know, I don't remember what it is. This is a good example. So 56 byte value 56 always means pushing this register. And byte value 55 always means pushing this register. So it stands to reason that there's also a 57 and a 58 and a 59 that are probably pushing other register values. And I give this up as an example. That might not be a good one to try and wildcard for, in that that might not be one that provides you with like a good code match. But something like, let's see, I'll go down here a little bit and see what's going on. So let me just try and see if I can find. I was going to try and see if I could find, probably if I look for this. Here we go. Oh, should pass that because that's special. So here's a great example. This case, so I've got XOR EDX, and then increment EDX, and then move EDX. So move the content of EDX into this memory location, then move this other one into EAX, then evaluate that. So this one's a great example because I think it has a this little thing that I got highlighted here actually has an example of every one of those three cases that I described. So this register EDX was chosen just because it's a good general purpose register. It's entirely possible that if I was to copy this code and paste it somewhere else, that the compiler may choose a different register than EDX, which would change this byte value here, and would change this byte value here, and would change this byte value here. So if you look up these instructions, so the move, increment, and XOR, if you look those instructions up on one of the references, one of the resources that's available over here, a number of them down here, plus I think maybe this one. So yeah, so this, and I think this is also available on the slide set for the lecture, but this is the I just grabbed the stuff that I have from last year's lecture on assembly language crash course. So if you look at this information here, you can find out what those byte values are supposed to be. So you can figure out how to do the wildcards and all that stuff. And you don't necessarily have to be perfect, because in some cases you might end up finding, for instance, if, go back here. So this one, for instance, if you were to do, we'll just say a byte pattern of like 4 question mark, that's really giving you the ability to match with one kind of token, gives you the ability to match 16 different values. But there may not be 16 different registers. That may not necessarily be a problem. You know, that might be broad enough, even though it's technically too broad. That, you know, the values that don't line up with registers that you can increment like that might not be instruction values that you typically run into in that context. So you can play with it a bit. But the idea is that you'd be able to just demonstrate using the wildcards, so that if you find a version, like if you find this sequence of data somewhere else and it happens to have been compiled to use ECX or EBX or EAX, or you know, any of the other registers that are available, that it still matches, or part of it still matches.
The instructions.
Yeah. Yeah.
We said we
Right.
registers.
Right. So go back here. And I'll go back up to the assignment. Come on. We have a there we go. So for this piece right here, you're probably going to be using a reference sample. If you use more than one reference sample, that's fine, but you'll be using at least one reference sample to build the signature from. So you'll be looking at the disassembly of one malware sample at least when you're building it, and that's in the paragraph above this. That's the sample that I mentioned here. However, just like in homework 2, you want to match on common code between the samples that you matched on from homework 2, or if you decide not to use those, you can try and hunt for a new group of malware samples, basically ones where you have at least 2 or more samples in the library.
So
Yeah.
you've been saying a wildcard specifically, but theoretically, couldn't you also be using using alternatives
Yes.
or statically sized chunks to do
Yes.
this as well?
Yep. Yeah, so, and that's what I have here. So the idea here is to just try and implement at least one of each of these. So you can implement more if you want, but try and implement, basically try and write a signature that implements at least, try and write signatures that implement at least, where at least one of each of those is used at some point. And it doesn't have to match one piece of code. So you might find out that you have one function where attacking it with the third one here, the binary data containing ranges, you might have one function or even one like section of the file where that makes a lot of sense. But then a different function doesn't make any sense.
Yes, in fact, I found one.
Yeah.
With the range.
Yeah.
But it's a function call.
Yep.
It doesn't really
So
these criteria.
yeah.
That's,
So that's, and you'll want to look at, basically we'll want to look at
yeah.
where each of them makes sense. And so kind of what I'm, going through here is maybe a little bit of hints on, so like in this one, it might make sense to try and match something where there's a, you've got like an XOR call like you have here, and then you have an increment following it. But just putting 42 is not going to match every increment. Putting 4 question mark will match the increment, but then we'll also match other things too. However, it's only going to match up to 16 different things. So that might not be bad. You don't necessarily need to be perfect. I'm gonna basically be running this against the, same sample set that I think I listed in here. Must not match on any legitimate Windows binaries. So I have the Windows XP and 7 VMs, and then I also have the Windows 10 VM, so all of which were pulled down from Microsoft's site. That's what I'm going to be using for my reference. I'm not going to throw in there random stuff like, I'm not going to run it on my personal Windows installation that has a bunch of other junk in it, and then knock off points for matching on some random random version of Firefox I have installed or anything like that. So yeah, but yeah, the different register arguments. What I'll be looking for is that variation exists somewhere. So I'm not necessarily going to be looking for it to be the case everywhere. I'll just need that variation to exist somewhere. And if I can't just find it in the samples that you provide, or I should say, a good way to guarantee that I do see the same variation being matched that you intended for it to match is to make sure that you add that in the description when you submit the Yara rule for the assignment. So there's like a little text box you can put in there, and you'll put the hashes in there, the samples that matched. If you do have any concern that I might not see the same matches that you see, feel free to put, like the offsets like that. So for instance, in OBJ dump, I can grab the runtime offset is available to me. So feel free to do that, or feel free to even like copy paste this, or from IDA Pro or whatever you want. So you can put as much content in that text box as you want. So, but yeah, that's what I'm talking about with the registers, is just to make sure that even feel free to copy paste the two different copies of code that you were matching, including the disassembly like this, and then that'll make it a lot easier, and I won't have to hunt it down, or I won't miss it. So the other one too I mentioned was memory offsets. So this is a great one. So you'll see that what this is doing is it's looking inside of the memory location that's listed here where my cursor is. And it's going to take the 4 bytes out of there, and it's going to store them inside the EAX register. So if I go, after I've sent this malware somewhere or whatever, or I should say, after I receive this malware from an adversary, and they realize that whatever their attack was has been shut down, one thing they might do is they might go back to this malware and try and change something in it, try and add code. If you add code, that's going to move things around in the file randomly. Anything after it or anything before it might get moved around, which means that whatever code or data that address happens to refer to might be moved somewhere else in the file. And as you can see, that data I have right there, that 100 C57C, it's actually hard-coded right here. So if the adversary goes and decides they're going to add like an encryption routine to something that previously didn't have an encryption routine, it's going to add code, and then it's going to push that data or function or whatever that is further down in the file, which means that when they recompile it with a new version of the attack, they're no longer going to have that address in the same place. Which means that when this thing gets compiled, that hard-coded address is going to have a completely different value. Which means that what I'd want to do is make sure that, while this move instruction may still happen, the address it's referencing may not. And the way that this works is that the address is these 4 bytes, and then the instruction to move 4 bytes from memory into EAX is actually encoded in this A1. So So you can kill two birds with one stone with this particular approach, because you can look up the move instruction on those documentation sites to try and see what possible different values. So other than just A1, because you can see underneath it that these other move instructions actually end up being 80 something and just above it. So there's a lot of different instructions, or I should say a lot of different byte values that map to move, and really they map to different versions of move. So you'll see that all these ones that start with 8 all have to do with certain types of move instructions. So 8.9 has the source as a register and the destination is a register indirect memory location. The two that refer to 8B, or the two that start with 8B, both of them are these register indirect sources with a register destination. So there is some consistency there. And looking through, you can even disassemble large amounts of files and just try and see what the patterns are that you come up with. Because if I was to throw like 5 or 6 different files at this and just have it give me all the moves, I could build up a nice like data set myself, just eyeballing it of what the likely values are. So for instance, if I did this, come on, right? So, and there's a little bit of data work and everything there. That's part of the, that's part of the analysis process, right? It's trying to figure out what these possible variations are going to be. So this one gives you a good example of the first bytes, either 8B, 8.9. Those are two very common ones, it looks like, just to me, in the 8 series. Then there's another variation that's either 8.3 or 8.1, which is another set. And then finally, there's a B8 that's here that looks like it's less frequent. That might not be consistent all the way down, like you can see right here. Whoops. There's the 8, well, there's more 8.9s and 8Bs. So you can look through this and you can try and see like what are the most frequent values. I can, chop this up more, and I can actually have, I can try and cut that first, this first byte value. I can try and run that through a filter that tells me maybe what the frequency counts of those are, which will give me the an idea of where to go when I'm writing detection. So and the reason I skipped over these is because these are really special ones. You can read about those, but what is going on there is it's telling the assembler that it wants to move only 16 bits from these 16-bit register selectors into these memory locations for whatever reason. So that's why I skipped over those. I don't know why this program is doing that. So anyway, yeah. So that is that's the reason, or that's kind of what I'm looking at for these. And then finally, I think I said immediate constant. So immediates are going to be like this thing. So I forget what the Intel syntax is, but the AT&T syntax is any number that has a $ is an immediate value. So it means use this number instead of use the data stored at this address. So it's basically store the number in AL for the one I've highlighted versus go to that address and then store the data at that address in AL, which is what it means when you don't have the $ or the immediate operator, whatever you want to call it. So likewise, this one up here, the fact that it's B6, that might just be some arbitrary value that it needs to be because maybe that's the length of an array or something like that. I don't, I can't speculate in this case, but that could very easily just be, some arbitrary value that came up at compile time, and if it were recompiled again, with say stuff moved around or stuff added or stuff removed, then the value of that immediate might change. A really great example of this is that sometimes, and many of you have probably written code like this for some of the assignments, especially if you have taken a network programming class or something like that. Very often a common approach with those things is a loop, an event loop, that when there's no action to be taken, sleeps for a defined amount of time. And usually you hard code something like 300 in there or something like that. You know, or I picked that as a random number for like 5 minutes or something, right? Code that's implementing backdoors very often is waiting for the remote operator to do input, so they'll arbitrarily pick, you know, the same thing, 300 or 88, you know, some number that makes sense, right? Or I should say some number that's arbitrary and long enough that it doesn't cause the CPU usage to spike, but also is short enough that an operator controlling the machine doesn't get annoyed with the sluggishness of it. So that's an example of something where if you're matching the value 300 that happens to be the sleep value, then if the adversary decides to change it to something like 301 or 22 or something like that, then you no longer match it unless you support kind of a wildcard for that case. And so that's one of the reasons why we're in the binary exercise here, we're wanting to use the wildcards. So anyhow, yeah.
So how would we identify that as an immediate constant from a memory address other than the size?
Oh, let me go back here. So in this case, I'll just do this. So this one is a memory address, and that's told to the processor by the A1 right here. So this A1 inside of that instruction, so the fields inside of that byte actually define the fact that it is a move instruction and that the source argument is an address. So the source argument is to be interpreted as an address, and the destination argument is the EAX register. So all that information is in the byte value A1. So if I looked up move, or if I looked up A1 on sandpile.org, which maybe I can try doing that. So if I think I go here, 1 byte opcodes, and then I go to A rate 1. So right here, remember, Sandpile's using Intel syntax, which is why they're flipped, but it's basically saying to use the accumulator register, or the EAX or RAX or AX, depending upon which version of the Intel processor it's on, and then move into it the value that's at that offset. So versus, we'll look at this one, right? So B1 would actually say move an immediate value into an immediate byte value into the CL register. And then, let's see. So what's really interesting here also is that if I go here and I read this, I can learn that, hey, the only variant of this that's actually expressed or that's actually implemented is moving from memory into the EAX, or moving from EAX into an offset. But I don't have an equivalent kind of single byte version of that for the other registers. So I would read into that maybe it's really unlikely for me to see that construction put together by the compiler. Or I might have to branch out and look for the other move instructions, which will be somewhere around here, I think. If I go here, I'm trying to remember. I haven't used this site for a very long time. So, oops. Yeah. So I might need to go and look into these or something. Okay. Yeah, there we go. Yeah, so here's, yeah, that's right, it's under the 8. So here's a whole bunch of other ones that I might want to go into. And this is 8.0, 8.1, 8.2, 8.3, 8.4, 8.5, 8.6, 8.7, right? So I might want to walk through here and actually find, and I may actually find that for all the other register combinations, there's actually a completely different opcode that move would be if any of them were to be put in there. And so maybe the compiler always writes the one version with EAX for that type of construction, for that type of algorithm. In which case I might, you know, might want to look at all the moves that don't have to do with that register. So likewise, this one is moving an immediate value into EBX, and in this case, BB and BD. Yeah, this is a great example right here, right? So this again, single byte move. The 4 bytes after it, these 4 bytes right here, represent this value. And then just by looking at this, I can see that these 3 different registers are being represented by 3 different move instruction bytes. So the first byte, the BB, BD, and B9, each appear to correlate to these different registers. And if I go down here and look at this one, I can kind of give better weighting to that. Like, you know, really what I'm doing right now is just like correlating the patterns to the different instructions right now. So you can see that BB looks like it's almost always EBX as the destination. B9 looks like it's almost always ECX. BE looks like it's almost always ESI. And then BD looks like it's almost always EBP. So I could go through this and try and find you know, how frequent it is. Or I guess the most frequent byte values, right? And then once I have the most frequent byte values, then I have something that's most likely to match that algorithm put somewhere else in the code. So like on these 3, if the registers were switched around, so if I took the registers and just shuffled them, but I left the immediate values in the same positions, then what would likely happen is I would shuffle these 3 bytes, but the other 12 bytes would stay the same. And that's the type of pattern that you're trying to match against. So I don't entirely know what's happening here. As you can see, this is actually running across many bytes. So there's actually instructions in between each one of these. So these aren't actually, I ran this through grep. So you're only seeing the filtered listing that matches what I'm looking for. But if we were to pretend for a second that these 3 were in a row, one possible reason for that might be that there's a function call that when the function is entered, it expects these 3 registers to have these values. That means, so if the function works that way, if the function has that expectation going into it, that means that you could actually have these 3 instructions be in any order you wanted to.
Well, the immediate values would be the same between 2 different.
Exactly.
hardware.
So no matter which order these 3 instructions were run, the immediate values would be the same. I mean, the immediate values in those registers would be the same going into the function, which would be another approach where you could, say, obfuscate the code a bit if you wanted to evade detection. So it's important to also recognize what algorithm is being implemented and whether or not there is a like a justification to the ordering of the data or not. So you know, one approach that I could use for this one could be the you know, basically doing like a B question mark followed by the 4 bytes, right? So followed by these 4 literal bytes. Like for whatever reason that might actually be significant, and then you know, and basically say have those in a row, or have a what did I call it here? I'll show you this thing. So I could also have them in between this, and I could have 3 of them, right? So I could do it that way too. The other thing, as I said, was that these 3 don't happen in this code right next to each other. They're actually offset by quite a number of bytes. So like AC, between this one and this next one, there's actually almost 16 bytes. It looks like there's about 14 bytes between the 2 of them. So there's probably one more instruction that is not being displayed to me right now because I ran it through grep. That's happening between them. So, you know, you might, when looking at the code, conclude that these 3 do have to happen in this order, but they don't necessarily have to happen next to each other. And to solve that problem, that's where the range comes into play. So, and I think they have some examples in the Yara documentation, but then there's also, I think, like, so Yara rules or something. Yeah, so there's also this. You know, which we can jump in here and maybe look at some of these things. And they have, I was hoping maybe I could find a good example of, let me try this one. Looks like these are all strings. So, I don't know. I could possibly go through a number of these and try and, I could do this all day and try and find them. But there's, you know, a large number of files in there. I know what I was looking for is in at least one of these, which would be examples of those features actually being used. So here you go. There's a great example of one right here.
Yeah.
So that one's got a good example of it. Oh, and then you also have the range used down here that basically says, you know, C7 followed by 2 to 3 bytes of anything, followed by 32, 32, 32, 32. So, you know, these are good ones to look at and to maybe try and see what they're doing. I'm trying to think, you know, in some cases, so this is a great one because, so if you remember back to the lecture where we were talking about doing malware research online, it's very common for a lot of these companies to publish on their blog information about these various different things. So for instance, this is securelist.com, so it's Kaspersky's blog. They have an entry on there, you know, blog entry on there, where they talked about something called Project Sauron or Sauron at some point. They might actually have this stuff analyzed on there. And if they do, then you can probably get some like a disassembly context to what led them, you know, to make those decisions. So, but you know, same's true up here. So, you know, again, it's right here. Unfortunately, they didn't put the full link in here for whatever reason. I guess I can go and try and see if this actually holds true or not. So, watch it. Oh, cool. Yeah, so it says, is blogging bad for you? Nice. So, let's see if I can actually find Project Sauron on there. So here we go. Published August 2016. So they have a full report. They have technical analysis. They have a whole bunch of other stuff. Download Yara rules, so you can actually get a copy of their Yara rules. You know, there's the key that's base64 encoded. These are really cool too because they'll kind of give you some insight as to the different methods that are used. But they don't have a whole lot of detail here. Probably it'll be in here. And look, it lets me download the PDF, so that's nice. So I could probably, you know, scroll down a bit here and try and see if maybe they actually explain why the disassembly they picked matches what it does, or the bytes that they picked matches what it does. I'm trying to see if I can find anything, but I can't. They have a large, so this is all really neat stuff because it talks about the different operations that are available inside of that back door and how to use it, etc. So that's definitely useful information. Trying to see. So anyway, I'll close that. You know, maybe I'll link that on the notes later on. So anyway, just you know, again, just like the other assignment, there is going to be a little bit of trial and error to try and narrow down. That's part of the analysis process too. Is you're going to hit something that you initially feel is like really good code, and then ends up not being great. One of the neat things is that sometimes you can end up finding that maybe the presence of 2 or 3. So basically, as you increase the number of blocks that you're matching on, so if you go through and look at like 4 or 5 or 6 different blocks of code, you'll start to run into the kind of co-occurrence, you know, property, which is that the more co-occurrent blocks of code that exist, the less likely they're to exist outside of that family, right? Until you finally get to all of the code, which you definitely won't have to do. But I will say that trying to dig into this, trying to dig into the EXEs that are available, one thing to keep in mind is that a lot of the code that's in there is going to be stuff that Visual Studio's added and stuff like that. And so that's where using like the free version of IDA Pro will come in handy. Or trying to navigate in, if you happen to be using IDA Pro or don't happen to be using it, it's not you know, it's not super critical, but you want to be aware of that. And whoops, I wanted to actually go here. Let's see if I got, yeah. Remember that this actually tells you, say, where the code actually begins. So let me see if I can remember. You know, the entry point is actually here, and trying to follow that in with whatever code analyzer you happen to be using is going to be super important. Or if you choose, you could run them in the VM in a debugger and look at it that way and try and find out when it gets to a steady run state where you break the program at. Running it in a debugger will also help you, and we'll be doing that next week. But running in a debugger will also help you identify which code the program's running in is from a library versus which code is from the main program itself. So, all right. Is that helpful? Yes.
I have two questions.
Oh, sure.
So first one is, can we move the submission date to Sunday?
Can we move it to Sunday?
We're not pushing that.
Okay.
Because like it's taking like too long to
Okay.
get something like really convincing. Because when we
Yeah.
did it with strings, I
Yeah.
could like really narrow down that, hey, I found this and
Yeah.
it's in my record. But when
Okay.
I'm trying to do this, I'm like totally lost everywhere.
Okay. All right. Let me see. Yeah, I can probably do that. It's due tomorrow evening right now, so yeah, I can probably agree to do that. So, as long as that's fine with everyone, I'm getting nods.
Here's what my
Yeah.
problem is. I did the claim scan on the samples
Mm-hmm.
in the EXE.
Yeah.
And I find a lot of, I'd say a lot of set of models and a lot of similarities, even in the name, like
Mhm.
Trojan underscore and anti FW.
Yeah. So that's
They have so
Trojan.
much, yeah.
So the clam AV will probably use a lot of heuristic signatures. That's what it sounds like. So the name, well, number one, I'll say the clam AV signature set has a lot of old data in it. So we'll say that. Also, just the properties that you described right now, it's telling you that it thinks it's a Trojan, which could mean any number of things. Basically, it thinks it's malware. Then it also has anti-FW or something, which may mean that it detected that it matches a signature for anti-firewall or anti-something else that FW abbreviates to.
Yes, that's the sample that I use in my
Yeah.
this, assignment too. But there's so much in common. I mean, when you said that the signature must have the different registered arguments, different address references. I thought you meant the match must occur at different addresses.
Oh, right. Like, for instance, this one must match in this location plus somewhere else. So, like, it must have more than one occurrence within the file. Yeah, no, the only thing I mean is just this, because this is going to be the content you're trying to match,
Yeah.
means that if they went and they changed up this with a different value, that it still matches if that happens to still be part of the algorithm. So, this is where I'll go back to the, there we go, this one. So, you know, actually, let me see. I think I still have the old version of IDA Pro on here. So no, it's gonna be here. Here we go. So is it IDA G? Maybe. Can't remember. I think that's it. IDA GUI. So I'll let this load up really quickly. So this is where and I'm perfectly happy to do. I've never run this in line on this VM yet, so give us a moment. Yeah. While this is loading up, yeah, I'll take another question.
For this third assignment, what I
Yeah.
was trying to do is, I found a matching string that was basically a call to an execute an exe file.
Yep.
And from the second assignment,
Mm-hmm.
and I was trying to find it in the third one.
Mm-hmm.
Is it that the right way to go?
Yeah, that's a totally acceptable way to do it. So there's multiple different ways to go about attacking the problem. That's the approach that I would have expected most people to try and take for the assignment, is to you identified strings from the or I should say you identified multiple samples already
Yeah.
that were supposedly the same malware family. So
Yeah.
it stands to reason that you can use those to just find the code similarities. And so then the problem becomes, okay, how do I attack the problem of identifying the same piece of code, even though it might be in two different positions within the two files, or the three files, or whatever.
The ones that I found, they have the same strings, the same imports.
Mm-hmm.
So
So what I'll do is I'll go out here and I'll go and open up that Miko blah blah blah, right? Guide you through advanced options. Sure, why not? I can't remember what this version allows me to do. Yeah, resources is fine. So this is basically just it loads faster if you uncheck some of these. It loads slower if you check some of them, or if you check all of them. So there's this padding symbol. Don't. Yeah. So as you can see, I didn't change much of anything. I just added the resources segment, which can sometimes be useful for this exercise. So because resources in Windows EXEs have the ability of having the code in the text section, or the code in the data section, but then you also have the resources, which is where icons and dialog boxes and strings and stuff are located. Sometimes those can just take up a lot of space, so it gives you the ability to skip loading those. For malware, it can be useful to load those because those tend to also be a place where malicious data is hidden. So some malware will actually hide EXEs in there. Other malware will hide configuration data in there, that type of thing. So when I was loading it in IDA Pro, or IDA Free, the only box I really checked was just to tell it to load the resources. So the reason I'm loading it up in IDA right now is IDA will give you an kind of an analog to what you were describing earlier, which is you use the so pretend you don't have the strings to relate the to easily relate the files together, or maybe you do have the strings. We'll go at it this way. We'll start with that way. Let's pretend that you do have the strings relating. I wish I could have a higher resolution. Give this a second. I wish I could have higher resolution on this projector, but instead I'm stuck with technology from 1998. So just give this a moment. There it goes. That's what I wanted to do. So then I'll go and drag this over here, and then it will take forever to render, maybe. Okay. Come on. There we go. There we go. So what this did is it put me basically at the entry point. What I can do is I can go here to the strings section, and if I found a string that was useful, like if I found a string that was significant or something like that,
and then I build my signature on those strings.
Yeah.
And found a lot of matches.
Yeah. Well, so one thing that why isn't this loading? Did I miss something here? Oh, it's over here, that's why. I'll just do this. So if I load up the strings, so it's got a bunch of the function names in here, right? But I might scroll down and find, here's a good example. Yeah, so if you find a complete sentence, this is the symbol for is processor feature present. I'm trying to see if I can find a good one. This might actually be a bad sample to do that because I think it has some, it's like encrypted or something. But anyway, what I can do sometimes is I can I'll go and grab like maybe this one. No, that's in the resources section. So this is a great example of one where the resource section actually has a lot of data, which indicates that it's probably let's see if I can go up here. Well, like, I think I double click on it, is that right? Yeah. So I double clicked on it and it took me to the disassembly view, or the what it calls the IDA view. So I was over in this tab, I double clicked on one of the strings, it brought me to the IDA view, and it showed me where in the file that string is listed. And so then I might like hit X on it to try and find out where it happens to be referenced in the code, and there's only one place. So this one's not a great one to work off of. But if you're using one of the string, I wish this wasn't so slow too. If you're using one of the strings, or if you're using one of the ones for which you had like really good strings data, then it would be a little bit easier. Let me see if perhaps this one, that's in our data section. So okay. I'm going to close this, and then I'm going to open up. I'm not going to. Oh, I should have said don't save the database. So, okay. Let me do this. There we go. There we go. I was just going to look at this one and try and see if, forget if this one ends up being any better. Yeah, unfortunately I don't, yeah, were I to have, well, we can just go over here. Source malware. So I think this one might be a good example. Yep, here we go. So this one's going to be a good example, right? So what I will do is I will copy, was this example, ex2. So I'm going to copy ex2 to my VM folder, and then what I'll do is I will load it up here. I'm going to cancel that, because I think one of the things that is slow on here is possibly the moving data between the two things. I'm also virtualizing Windows, which itself is small, but let me do this. cp so I'll get that onto the virtual hard drive, which probably will make it a little bit easier to interact with. And then let me just here maybe. That's right. Do that, and then I'm going to go here, and then here, right? So that loaded up a lot faster. So it put together the main function and everything like that, right? So I'll go and load the strings window up. And you can see that there's a whole bunch of these function names are in here. One of the useful things in here, how to kind of interpret this, is that it shows you which section that the strings are showing up in, right? Let me move this over a little bit. For some reason it's not rendering the scroll bar, but I think that's just an artifact from Windows. So I don't really care too much about our data is going to be like relocation data. So it's data that's useful for the system that is responsible for hooking DLLs up, or I should say functions and DLLs up to your application so that you can call code that didn't get shipped with the application. But then the interesting thing is that there's all these different things here. So, you know, I go through this and I would look at it. This looks like a dictionary of some sort. This also looks like a dictionary of some sort, possibly the same dictionary. This one looks like an English sentence. I didn't actually sign this for an assignment in this class, so I'll just tell you this one also, this is a 26 character string. It's a substitution alphabet. So this is also a dictionary basically. So where, you know, T maps to A, H maps to B, E maps to C, like that type of thing. It's a substitution cipher. Which means that the code to implement the substitution algorithm needs to refer to that somehow. So if I'm curious, I'm looking for anything that has that, you know, hypothetically, this doesn't have to be in this order. It could be in any order, just as long as the source and destination agree, right? So if I was to look for this particular substitution alphabet, that would only be able to detect code or detect implementations that use this specific alphabet. If I swapped T and H, then I wouldn't be able to detect anymore. I wouldn't be able to identify it. So what I might do is I might want to go and find out where in the code that alphabet is referenced. And then where that alphabet is referenced is most likely going to be the code that is responsible for doing the math to basically translate from encrypted to decrypted form and back and forth. I'll say that what you can see up here is you can see that that alphabet's actually referenced in two functions, which probably means that there's the incoming stuff, so there's a decryption function, and then there's probably also an encryption function. Or maybe there's just two decryption functions, I don't know. But you can go to either one of them. This one might be a good experiment because it looks like maybe they copy-pasted the same code somewhere or copy-pasted a very similar amount of code. So maybe you have two implementations of the same algorithm in the same file. So this would be a really good example of one to look at. Unfortunately, because I am forced to use this really, really terrible resolution, this is going to be kind of difficult to see. But this is where IDA Pro helps you because it helps you kind of navigate and put the dots together. But you can see that that is referenced here. And using this graph over here, you can see one of the secrets is they highlight with bold lines or with thicker lines. They highlight sections of the graph that are actually looping back on themselves. So sections of the graph that probably implement loops are always highlighted with a much more, with a much bolder edge than the ones that are merely just single path. Was it single traversal paths or whatever? So in this case, one of the other things I learned about this is that both of those alphabets or both of those dictionaries are used here for whatever reason. So this one's also used here. So it gives you the ability to actually see what the full thing is, because this is just a summarized version of it. The full string is basically all the uppercases, all the lower cases, all of the numbers, and then 3 symbols, which is going to be 26 plus 26, which is 52, which then is 62. Yeah, and then basically ends up being 65 characters, or base 64 followed by the equal sign. So and so this ends up most likely being a substitution cipher for a, or not substitutions. Well, I mean, actually, it's a very low-tech one. It's basically an alternative representation of a base 64 algorithm as well. So my read on this is that you end up having an algorithm that is implementing a modified base 64 decode that also, for some reason, is using this plain text substitution cipher. That seems pretty unique to me. And there's going to be a number of mathematical operations that happen in here that are very particular to this. And so as you go through here, you'll actually be able to see those things. So for instance, yeah, it's, and then it's, yep. And so then it also has this call EBP here for whatever reason, which probably ends up getting populated up here, yeah. So that's another thing that's interesting too, is it took the address of the string to basically search for a character in the string, give me the position of a character in the string. It stored that function in EBP before it got into this loop, and then it uses the register call here and here as almost like a shorthand. That itself might also be another significant trait that's not very common, I'm not sure. So, but that would be an example of how you use the, the Yara signature matches that you're able to build in part 1 to then branch out and make a binary signature that will possibly match code that may use the strings or maybe use something else that's in the file. In this case, if I'll go back and hover over this base 64 string here again and point. Oh, I actually need to do that, don't I? Or maybe it's this. There we go. So this, the normal base 64 alphabet is, it's all the uppercases, all the lower cases, plus the numerals plus 3 symbols. Usually I think it's like slash, hyphen, and equal sign, or slash plus and equal sign. I can't remember. I think it's slash plus and equal sign. That's the typical one when you run base 64 on your computer, or when you're dealing with base 64 encoded data that happens to be in an email or something like that. So what they ended up doing was they ended up picking 2 different characters for some of the symbol characters. They could arbitrarily pick any symbols that they want. You have, at least like, 15 of them on the keyboard, right? So looking at the algorithm and the combination of these 2, so looking at the algorithm that combines the 2 of them and building a signature for that means that the code that's responsible for implementing this is something that you can write a signature to detect, and then have something that's longer lasting than just looking at the dictionaries, because that way, no matter what dictionary the bad guy decides to choose, because he doesn't, or I should say, they don't have to change just the symbols. Hypothetically, the entire base 64 alphabet here is within their control. So they could choose to swap the lowercase and uppercase characters, they could choose to shuffle them all around if they wanted, just as long as the dictionary is the same on both sides. Because at the end of the day, it's really just what represents slot 0, 1, 2, 3, 4, etc. on here. So, and that's kind of why that's kind of why there's a large amount of value in doing this kind of binary analysis and then trying to build signature detection around the binary functions and the binary code and the binary algorithms that are implementing a lot of this stuff. Is that if you look at it from the perspective of a maybe author of code or something like that, the person who wrote this algorithm in the first place may have written it once and then given it to some people, and then there's a large number of people with basically a passable competence in compiling things in C++. A lot of those folks it would be very trivial for them to change these parameters around. It may be a lot more difficult for them to actually try and modify the algorithm so it behaves differently. They might be more likely to break something in that case. So the thing that's likely to change in the future, because that's how this whole game works, right, is that adversary writes an attack that works, attack works for a period of time, attack stops working because someone figures out how to detect it and defend against it. Adversary goes back to the table, says, hey, I'm going to rewrite it, and I'm going to keep trying to rewrite it, keep trying to iterate it until I get something that works again, an attack that's successful again. And that one works for a while. And then it gets detected or it gets investigated. And then somebody builds up a way to defend against it. And then go back and they work on the tools again. So it's basically a back and forth cat and mouse game type of thing. So the question is, what makes that return to development cycle a lot more costly for the adversary? And that's what you're trying to do from like signature detection standpoint. And that's what this exercise is trying to put together.